Well, thanks very much, and we're just 1 minute late in starting, but I'd like to thank our speaker, Xin Qiu. Is that right? I'm not very good at pronouncing names. Okay, good. And the very interesting paper that she has recently had accepted at Biometrics on estimation and evaluation of the linear individualized treatment rules to guarantee performance. I'm not an expert on this. I found it very interesting to read this. So what we do in the Journal Club is we try to keep it very simple, hopefully. We don't want to be too technical, but we are interested in hearing about this paper. The audience are welcome to make comments after the presentation and after the discussant has had a chance to discuss the paper. But try and keep it short, keep your questions concise. If you have a question, please type, say so in the chat box down to the left, on the lower left, and I will try and introduce you and ask you for your question when the time comes. Try to speak slowly and clearly. The internet may not be the best, and the English may not be optimal, but we should be able to understand each other. Try and be constructive. This is a discussion that we want in a positive way, and respect others. When other people are speaking, perhaps we can ask you to mute your microphones so we don't get lots of background noises. So finally, the paper and the supporting documents are available through the registration email. I'm not quite sure where they are on this particular screen that I have, but the session will be recorded and they are available on the IBS website afterwards. So please feel free to have a look at this afterwards using the IBS website. Okay, with no more to do, I shall now introduce Xin Qiu, and ask her to take over as presenter and present her paper to us. Xin, are you all right?
Mm-hmm.
Okay.
Thank you for the introduction. All right, this is Xin. I'm from Columbia University. Before we get started, I would like to thank Dr. Todd and Christina for organizing and inviting me to this journal club. And I would also like to thank today's discussant, Dr. Wang. Also my two co-authors, Professor Donglin Zeng from the University of North Carolina, and Professor Yuanjia Wang from Columbia University. My topic today is estimation and evaluation of linear individualized treatment rules to guarantee performance. As we all know that clinical practice today still remains largely empirical. Treatment for a patient is often based on physicians' past experience with patients of similar medical history. However, treatment heterogeneity does exist in a lot of chronic diseases such as major depressive disorder. Personalized medicine refers to tailoring of medical treatment to the individual characteristics of each patient. It is necessary since heterogeneity in response does not only exist across patients but also within a patient, which means that a treatment works for now may not work for another. On the other hand, a treatment works for one patient may not work for another. So the goal of personalized medicine is to provide each patient with the right medicine at the right dose and at the right time. So what statisticians can do is to use individual characteristics to learn an individualized treatment rule for each patient so that clinicians can use the decision rule as a guide to provide best clinical care for patients. There are three types of variables that might be useful for learning individualized treatment rules. In this plot, it shows how treatment effect changes across the covariance X. On the left, in this figure, it is a prognostic variable, which is only associated with the outcome but has no interaction with the treatment on the outcome. In the middle is a predictive variable, which has qualitative interaction with the treatment on the outcome. On the right is a prescriptive variable, which is most useful in tailoring the treatment because it has qualitative interaction with the treatment on the outcome. Basically, the treatment effect changes the direction as the covariant X changes. There are some existing regression-based and machine learning methods. Here are some of them. For example, Q-learning is a regression-based model which focuses on modeling the Q function. This method proposed by Zhang and co-authors estimated the optimal ITR by directly maximizing the value function over a specified class of treatment rules through either inverse probability weighting or augmented inverse probability weighting. The later one is called double robust estimator because it is more robust to the model misspecification. The virtual twins method uses a tree-based estimator to identify subgroups of patients who show larger than expected treatment effect. O-learning is another popular method which directly maximizes the objective function by transferring it into a classification problem. Recently, Huang and Feng, they proposed this robust kernel method, which is similar to O-learning, but uses a more robust approximation for the zero-one loss in solving the weighted support vector machine problem. They considered a binary outcome, and they try to minimize the total burden due to disease and treatment in their paper. Interaction trees and qualitative interactions are both tree-based methods, which focuses on identifying interactions between treatment and feature variables on the outcome. As we know, one of the disadvantages for the regression-based method is model misspecification. In reality, true optimal ITRs can be very complex and depend on large number of predictive or prescriptive markers. And also, it is not realistic to assume that all markers are measured in practice. So ITRs fitted in finite sample can be easily misspecified due to limited information collected. So we believe that all decision rules are likely to be misspecified in the complex practical application settings. Therefore, a clinical useful rule should be simple and interpretable, such as linear rules or decision trees, and at the same time, it should maintain certain optimality to benefit patients. So our goal in this work is to develop a method to derive a simple and interpretable rule, which is optimal among the class of similar rules, and perform diagnosis on the estimated rule. Next, let's see the notation of our work. In this work, we will focus on single-stage randomized clinical trials with continuous clinical outcome R. A treatment rule denoted by D of X, which is the sign of a decision function fx. It maps from the covariance space X to the treatment space -1 and 1. So the value function of a decision rule is defined as the expected clinical outcome is defined as the expected clinical outcome following the decision rule D of X. This value function is usually the objective function that we would like to maximize to find the optimal rule. Next, we define ITR benefit here as the difference in expected clinical outcome by following the decision rule d of x, or not following the rule d of x. A two-step method could be used to estimate this ITR benefit. First, you will just estimate an ITR, and then the next step is based on the estimated ITR, you could use the empirical mean difference of the clinical outcome between those who follow the estimated rule and those who do not follow the estimated rule. And this benefit can be estimated for both overall sample and pre-specified subgroups. Later, we will use this ITR benefit as a diagnostic measure to evaluate the optimality of a candidate's rule. We will talk more on this later. Now let's talk about how to estimate a linear ITR. The existing method, as I discussed before, is O-learning, which is directly maximizing the value function, this one, by using weighted support vector machine. In their method, hinge loss was used to approximate the 0-1 loss in solving the SVM. However, hinge loss is widely used because it is a convex loss and therefore it is computationally efficient. However, the misclassification penalty for hinge loss is unbounded, so O-learning may not be optimal when we only consider the linear decision rules. In our paper, we propose to use ramp loss to replace the 0-1 loss in SVM as an authentic approximation to the 0-1 loss. It will ensure more consistent benefit estimation. So let's take a look at this figure. In this figure, we compared hinge loss, ramp loss to the 0-1 loss. As you can see, the solid black line is the ramp loss, which is bounded by 0-1, and as the slope goes sharper and sharper, it actually converges to the 0-1 loss, while for the hinge loss, because this part is not bounded, so it'll never converge to the 0-1 loss. Later, we have shown that this rule, the proposed rule, converges is asymptotically optimal within the class of all linear rules, so we will just call it asymptotically best linear O-learning, short for ABLO. In this slide, we will show how to estimate an ITR using ABLO. In order to deal with negative outcomes and improve efficiency, Liu and other co-authors, they have proposed to use residual, like so, to replace the outcome in the weight in estimating the ITR. So with some calculation, we were able to show that maximizing the value function is equivalent to minimizing this penalized weighted sum of ramp loss, like this. Here, this HS is the mathematical form for the ramp loss. And this S is a tuning parameter which can be determined by cross-validation. As mentioned, that this ramp loss is not a convex loss, so solving the optimization problem is a bit difficult, but we could always use the difference of convex function algorithm to solve it by decomposing this ramp loss into two convex functions, and then using the iteration of quadratic programming, we can estimate the the ITRs here. Now that we have the linear rule estimated, the next step, we want to propose a diagnostic measure to evaluate the optimality of the proposed rule. First, we define this F star X as the treatment effect given X. Then the sign of Fx is just the optimal treatment rule. So if an estimated ITR F hat is optimal, then it should have the same sign as this F star X. With some calculation, we were able to calculate that the benefit of F hat X is actually the absolute value of the treatment effect F star X, which is always greater or equal to 0. And this is true for any subgroup C. On the other hand, if we know that the subgroup ITR benefit for F hat X is greater or equal to 0 for any subset C, then this F hat X must have the same sign as the F star X. So the conclusion here is that optimal rule is expected to have a positive benefit within every subgroup. In practice, ITR benefits can be used as a diagnostic measure to evaluate the optimality of a candidate's rule. For example, if subgroup ITR benefit of a decision rule is positive for a rich class of pre-specified subgroups, then we may conclude that the rule is optimal or close to optimal. Next step, we can use the diagnostic measure to propose some tests for the optimal linear rule. First, we can test the significance of optimal linear rule compared to non-personalized rule by testing whether the overall benefits for them are the same or not. Here, this delta 0 is the benefit for the non-personalized rule. And then we could also check the heterogeneity in ITR benefit across different subgroups by testing whether the subgroup ITR benefits are equal or not with the HTB test statistics like so. This HTB test is useful in identifying the subgroups that an ITR doesn't work as well as other subgroups. In practice, we estimate ITR benefits using an independent sample to guarantee an honest measure. Here are some theoretical results that we will not talk in detail. First, the linear ITR estimated by ABLO converges to the true optimal linear rule asymptotically, as we mentioned in the previous slide. And then another conclusion is that the estimated overall and subgroup ITR benefit converge to the true ITR benefit asymptotically with an asymptotic normal distribution. This result actually is used to guarantee the statistical inference in the previous slide. Next, we performed some simulation studies to evaluate the performance of our methods comparing to other methods. Here is the simulation design. It is pretty complicated. I'll talk about it briefly. Basically, we have informative variables and noise variables to construct 4 latent groups. And within those groups, we have 3 variables useful for generating the clinical outcome based on different treatments assigned. And for those 3, two of them, W and Z, are observed, while this S is latent variable. We will use all the observed variables to do the analysis, but this S is not observed. We compared our ABLO method to O-learning, Q-learning, and predictive modeling in our simulation. The predictive modeling works in 3 steps. First, we need to apply random forest regression on the outcome to the treatment, and Z represents all the observed feature variables. And then we can predict the outcome given different treatment and given their feature variables. And the next step, we can estimate the treatment difference given the feature variable. And in the end, we will estimate the treatment, the optimal treatment, with the sign of the treatment difference. The Q-learning method is similar to the predictive modeling, except that in the first step, it applies a linear regression on the clinical outcome to the treatment and the feature variables. We tried 2 sample sizes, 800 and 1600. We ran our simulation 500 times with cross-validation. We also compared the estimated rules to the global optimal rule and the best linear rule. For the global optimal rule, because it's a simulation, so we were able to generate the clinical outcome under both treatment, and we were able to know which is optimal and which is not. So we can calculate the benefits based on that. For the best linear rule, we computed it by numerically maximizing the value function under our simulation models. Both rules the benefit for both rules were calculated based on a large independent data set, different from the simulation data set. So next, let's see the results. Here we plotted the overall mean benefit on the left and the accuracy, classification accuracy on the right. Basically, the black line here, it represents the ITR for the global optimal rule, while this red line represents for the best linear rule. As you can see here, our ABLO method gives a more robust and accurate benefit estimation, and also here the ABLO gives the most accurate classification rate overall. And the next, we check the subgroup ITR benefit by one of the observed variable W. It shows similar results comparing to the overall results, because this ABLO method always gives us a better estimation of benefit, of subgroup benefits, and it works better when the sample size increases. In this slide, we try to check the heterogeneity in ITR benefits for different variables using the HTB test we proposed before. And for those 4 variables, W has strong heterogeneity, X1 has weak heterogeneity, while V and U1 has no heterogeneity. If we take a look at W, we can see the ABLO always gives the biggest power here, while other methods doesn't work so well. And if you look at U and V, we will see that ABLO, the type 1 error rate for ABLO is controlled pretty well at around 0.05, while the results for other methods are kind of conservative. Next, we apply our methods to a real data example. The study data it is from a randomized trial to compare various treatment regimes for patients with major depressive disorder. The study design for the study is pretty complex as shown here, but we will just focus on level 2. The goal of this study is to minimize the clinical outcome, which is the quiz score at the end of the level 2. Quiz score is a measure for the symptom of depression, which is the lower the better. We compared two treatments. One is treatment with at least one SSRI, and the other is treatment with no SSRI. Here are the variables that were included in our analysis, and we have 788 patients in our analysis. Again, we use cross-validation and repeat the procedure for 500 times, and this is the overall results comparing other 3 methods to our ABLO methods. Apparently, our ABLO methods has the biggest overall mean benefit and also the lowest value function, which is the quiz score. So both are as desired. So our methods perform the best in this real data application, meaning that if patients follow the ITR estimated by ABLO, they will achieve better treatment response by the end of the level 2, comparing to follow the estimated rule by other methods. Next, we show the results for subgroup ITR benefit by the baseline quiz score. This is the mildly ill group, and this is the moderately ill group, and this quiz greater than 16 is the severely ill group. Basically, we can see that the proposed ITR works well on the mildly ill and the severely ill groups with large benefits, while for this group in the middle, it doesn't work well because the benefit is almost negative. So the next step, we will try to use our method to work on this subgroup only to see if the rule could be improved or not. In this work, we propose to use ITR benefits as a diagnostic measure to determine the optimality of a candidate's rule. ABLO is considered as an improvement of all learning with robust estimation of ITR when an ITR is misspecified. In the future, we will try to develop this ABLO method to estimate dynamic treatment rules from SMART trial, and we will, motivated by the last application example, we will also try to use a data-driven method to identify important subgroups and learn ITR simultaneously. Here are some selected references, and thank you for listening.
All right, if you want to go ahead and proceed, I'm here if you need any help with this, okay?
Okay, I'll do that.
Thank you.
Hello, everyone. This is Xin Qiu from Fred Hutchinson Cancer Research Center. Today I'll be discussing the paper by Qiu, Zeng, and Wang. First, I want to congratulate all the authors for excellent paper, and I want to thank Dr. Todd for the invitation and Christina for helping me set up. So today, I basically want to highlight a few points in the paper and mostly talk about my thoughts about its possible relation to existing work and clarify their difference. So basically, in Qiu and all 2017 biometrics paper, the target is the development of a linear individualized treatment selection rule basically in treatment selection, we often have a value function we are interested in to optimize, which is like the VD here. And in their paper, it was reduced into an equivalent problem of minimization of a residual weighted misclassification error problem, where one could minimize an empirical version of it, which involves a W term, which is a residual, which is the outcome minus R hat. R hat here, where R hat is from a working model by regressing this outcome uncovert. So the estimator of this treatment selection rule is then obtained by minimizing a penalized weighted sum of a ramp loss estimator. In this, as Ms. Qiu has presented, the advantage of the tableau estimator has been demonstrated in numerical studies and in the data example, compared to several existing estimators of individualized treatment selection rule. Specifically, I want to touch base on this O-learning estimator because it's basically in the same paradigm of minimizing a misclassification error rate. But the difference between the O-learning and the proposed estimator is that they use different weights. In the O-learning, they use the outcome rate, and also they use a different loss function. For this 0, 1 loss, hinge loss was used in the current paper, while in the O-learning, while the ramp loss, which is a better approximation for 0, 1 loss, was used in the Qiu et al. 2017. So I have some thoughts on some related work and about like how it could be related to the current methods. Also, one reference as also pointed in the paper is Zhang et al. 2012, where they proposed maximizing the value function within a pre-specified family of treatment selection rule. So basically, by framing this problem as a missing data problem, we consider two different weights for estimating this value function. The first is the inverse probably weighted estimate. The second is the augmented inverse probably weighted estimate, which was called AIPWE. Basically, this weight compared to the first weight is like the augment the first weight IPWE estimator with a term that relies on estimation of this model of this outcome conditional on this covert. So this has the same flavor as what we have here in the tableau estimator, because they also require estimation of a term that rely on this working model. So similarly, as pointed out in Huang and Feng 2014, this maximizing problem can be characterized as a problem of minimizing weighted classification error in that form, and where the weight could be derived using either this inverse probability weight or this augmented inverse probability weight method. And it actually has been shown that the O-learning estimator is actually equivalent to the IPWE estimator. And in Huang and Feng 2014, they used the penalized weighted ramp estimator for deriving this individualized treatment selection rule, and show that if you use ramp loss, it performs better than hinge loss. And also, if you use AIPWE weight, you can perform better than this IPWE weight in some scenarios, even under a misspecified model. So my question here and some thoughts here is really this AIPWE weight and estimator and the tableau estimator, like how are they related, since they really have some flavor. They both rely on modeling of the outcome conditional with covert, and they both outperform the outcome weighted O-learning estimator. My next, I basically will touch base on the benefit function proposed in this paper. One major contribution of this Qiu et al. 2017 is that they actually proved a symptomality of the penalized ramp loss estimator for linear ITR. And it also proposed a benefit measure for the ITR, which is denoted as delta Fx here, which basically is the difference between the value function if you apply the recommended treatment selection rule to everybody versus if you just do the opposite of the treatment selection rule. And they have proposed to use this benefit measure, delta, to do three different things. One is for test significance of the optimal linear rule compared to a non-personalized rule. The second one is to test heterogeneity of this benefit measure across subgroups. And third one is test the non-optimality of the best rule in subgroup. So basically, I want to point out some relation of this measure and existing measure and how they're actually doing different things. So first, what is this delta measure? As I understand, it's really a diagnostic measure for global optimality. As Ms. Qiu has also mentioned, like for global optimality, if you have a global optimal rule, then you should always have its delta value greater than or equal to 0, which means that you can see how close your best linear rule is close to the global rule, but just see whether your the delta value for your particular rule is always have value greater than or equal to 0, or it can go the other way. So then, what is the clinical meaning of this delta measure? Since it was proposed as diagnostic measure, does it also have a meaning that's really meaningful in clinical practice? To think about that, I want to first just bring up another benefit measure that has existed in literature, which is called expect benefit, which is just a simple measure. Its definition is just the value function if you apply your ITR to the population minus the value function in the population. If you just simply give everybody the same treatment. So basically, this expect benefit measure is clinical meaningful measure because it tells you that in what's the benefit in terms of the value function you are interested in by applying this biomarker-based treatment selection rule compared to if you just have a rule that does not use biomarker and treat everybody equivalently. So I did some simple algebra work and found it's actually this benefit measure, proposed measure delta has some simple relationship with this expect benefit measure. So basically this delta will equal to 2 times this expect benefit plus the delta 0 term, where the delta 0 term is just the difference in average value function in the population if you treat everybody minus if everybody did not receive the treatment. So now look at the 3 different hypothesis tests we want to perform. First is the paper proposed that we use delta Fx to test significance of the optimal linear rule compared to non-personalized rule. Look at like the H0, that's their difference greater than 0 versus H1, H1 greater than 0 versus H0 is there is no difference. So actually, based on the formula I just showed in last slide, we can show that this term, the difference between the optimal linear rule compared to non-personalized linear rule is just proportional to the expect benefit. So that here, if you do this test significance of the optimal rule compared to non-personalized rule, it will be equivalent to do an inference just by testing whether your expense benefit is equal to 0 versus it's greater than 0. So for the second question, for test the heterogeneity across subgroups, first, like if we think about we have exact benefit, we can actually just test its heterogeneity across subgroups. What that test is telling us is how different this biomarker-based treatment selection rule is improving over a non-personalized rule across different populations. So you will know maybe, for example, in certain subgroups, having this biomarker really helps improve the benefit of the whole population versus in some certain other subgroups, using the biomarker doesn't really help. Now let's look at like heterogeneity. If we want to test heterogeneity of the delta, because delta is actually equal to 2 times its benefit plus delta 0 term. So the heterogeneity of delta really have a quite different meaning from the heterogeneity of expected benefit. So my understanding seems like the heterogeneity of delta is really telling you about across different subgroups how close is your linear treatment selection you're doing compared to global optimal. So it basically says that maybe in some subgroups you want to further improve your rule, but in some subgroups maybe this rule is good enough. So even if they're all called benefits, they're actually telling you totally different things. So the third part is about the test the non-optimality of the best linear rule in a subgroup. I actually think this is like what this delta is really important here. So the paper has used that for in the data example, but not in the simulation. So I'm very interested to know more about this test in terms of, for example, its power, and like in practice, how can you determine your subgroup? Would your choice of the subgroup actually impact your power? Even more, like when we think about like we have the choice between a linear ITR versus nonlinear ITR. Is linear ITR good enough? You can think of like when you want to test whether linear ITR is good enough, you can just test it in whole population with normality, or you can actually cut it into different subgroups. So again, like if you want to have a good power to know whether this linear ITR is good enough, is there a way, like any thoughts to handle curse of dimensionality if you actually have like several number of coverts available? And also another question is upon like rejection of optimality, like any thoughts about in practice, would you prefer to replace that with a more flexible nonlinear rule in general, or you just try to refit ITR within specific subgroup? Again, how do you choose a subgroup? I think that will be a quite open question to consider. So my last question is really about like it's nice that this paper proves the symptotic distribution for linear ITR rule as made. I imagine this distribution theory for nonlinear ITR will be a much challenging problem, and I will it'll be really interesting to see in the future if there's any progress on this part. That finished my discussion. Thank you.
So I'm actually just going to go ahead and take some of the questions on the Q&A section. So we do have a question from Yang Li. Dr. Qiu, is whether the proposed this is for Dr. Qiu, is whether the proposed method would apply to a general decision function or a decision function with an unknown form. In the paper, a linear decision function was considered.
Question: does it apply to a general decision function? Yes, our diagnostic measure can be applied to any general decision function, because when we derived the diagnostic measure, we didn't use the linear decision function.
Okay, and that question came from Yang Li. Yang Li, does that answer your question?
Oh, can you hear me?
Yep, we can hear you.
Hi. Yeah.
That answered your question? Okay.
Thank you.
All right, perfect. Well, thank you so much for that question. We do have another question from Dr. Thomas. His question is, my understanding was that the optimal rule is guaranteed to be better in every subgroup. What is the importance of testing for heterogeneity? And since every subgroup has an advantage, why would we care about heterogeneity across subgroups?
We are testing the heterogeneity basically for our linear rule, because for linear rule, we know that in most cases it will not be optimal globally. So we want to know, like, for which group it is better, performing better comparing to the other subgroups. And also in clinical practice, there are certain clinically meaningful subgroups that we are interested in knowing whether the rule performs better or not.
Okay. And Dr. Thomas, did this answer your question? If you're still on, you can feel free to elaborate if you have more. Okay, I'm just going to go ahead and quickly check to make sure there's no more questions in the queue, and just bear with me for one moment. Well, it doesn't. I don't have any questions at this time. However, if anybody has any, I'll give it a couple more seconds just in case anybody has any that they'd either like to chat over or voice now. Now is the time. We'd be happy to take them, and we'll just give that a few seconds. Okay, and it doesn't look like we have any more questions at this time. So we really do appreciate both our speaker and our discussant for coming in today and giving us this presentation. It was fascinating, and we hope you all enjoyed it, and we hope you all will attend our next journal club, which will be happening in June, and we will announce that and give you further information at that time. So with that being said, I'm going to go ahead and close this meeting. And again, we greatly appreciate both our discussant and our speaker for attending, and everyone for attending and speaking today. We really appreciate it and hope you all take care.